Hi everyone, in this video we are going to practice doing 3 different types of half-life calculations. So let's dive right into the very first one. If we tell you that the half-life of cobalt-60 is about 5 years, how many grams of a 100 gram sample will remain after 21 years? Go. Alright, did you get an answer? Hopefully you did. I'm going to show you how I personally approach this problem, but what you'll see with half-life is that there are about 1,000,000 different ways that you can do this, but I'm just going to show you the same method every time because it's what works for my brain, okay? Alright, so the first thing that I do is I look at my total amount of time. So it says that we have 21 years total. So what I like to do right away is figure out how many half-lives are we talking about. So what I do is 5.2714 times something has to be equal to 21. And for this case, it's approximately 4. Okay, this has to be a real number. You can't say 4.2, 4.8. It needs to be just a full integer value. And so this is approximately 4. So now we're saying that we start with a 100 gram sample. So what we need to do is very, very slowly figure out how many grams are going to be left over at the very, very end of 4 iterations. So we start off with 100 grams, and then we're going to do one half-life. The first one is going to divide our sample in half. So 100 divided by 2 gives us 50 grams. So after 5 years, we have about 50 grams. But we need to do this 4 times. So that was our first one. Our second one, we divide 50 by 2. We end up with 25. We have to do a third one. We divide 25 by 2, and we get 12.5. We have to do a fourth one here, and in order to do our fourth one, we need to divide 12.5 by 2, and that gives us 6.25. Boom, we're done. That's it. That's all we had to do. So we had to first figure out how many half-lives we have. Then you start with your starting material and you simply just continuously divide by 2 until you hit the right number of half-lives. So for us, this answer is just 6.25 grams. Easy, right? Maybe not, but just don't get frustrated. Sometimes half-life just doesn't work for some people's brains for whatever reason, but all you have to do is practice, practice, practice. The more examples you do, the better you'll get at this. So let's try another one. This way's a little bit backwards from the first problem we just did. So now I'm telling you that phosphorus-32 has a half-life of about 14 days. After 57 days, we know we have 10 grams of sample remains. So how much did we have at the very, very beginning on day 1, hour 1? Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's okay. This is kind of a backwards way of doing the first problem. So it's very similar, except for instead of starting with a certain number, now we know how much we end with. So it's just backwards. So what we need to do first, though, the method doesn't change, is figure out exactly how many half-lives our sample has gone through. So we know that it has a half-life of 14.29 days. We need to multiply that times some number, and that will give us 57. The only number that we can multiply 14 by to get 57 is 4 approximately. It's a little over 4, but we need a full integer value. So now what we know is that at the end of all these half-lives, of these 4 half-lives, we end up with 10 grams. So we have to work backwards here. So we're going to start with 10 grams, but meaning that is what we ended with. So instead of dividing by 2, we're multiplying by 2. God, I hope this makes sense. All right, so we're starting with 10 grams, which is what we ended with. So then after it went through one iteration, we're going backwards, right? So we're going back in time. So on day 57, this is day 57, you have 10 grams. But now we have to do 57 minus 14, which gives me 43 on day 43. We're actually at double that, so 20 grams, and so on and so forth. So that's our first half-life. We have to do this 4 different times. So 20 times 2 is going to give me 40. That's our first half-life. Second half-life. Our third half-life, 40 times 2 gives me 80. We have to do this one more time because we have to do 4 half-lives. 80 times 2 gives me 160. So on day 1, we had 160 grams. So it's the exact same process that we just did on question 1, except for working from the forward to end. With this problem, we work from end to forward. And so that you just have to understand that we're multiplying by 2 instead of dividing by 2. And it's all in the context of the question. So for the first question that we had here, it told us that we have 100 grams of sample at the end, okay? Or at the very beginning, we're trying to figure out how much we have at the end. But for this question, we're saying we have 10 grams of sample at the end. How much do we have at the beginning? So the context of the question actually tells you, are you multiplying or dividing by 2? You have to be able to figure that out just by looking at a question. All right, so now we're going to end with something even more fun, which would be radioactive carbon dating. And so what we're going to do here is try to figure out how old a fossil is that has a carbon-12 to carbon-14 ratio of 2.5 times 10 to the 11th atoms of carbon-12 to every 1 atom of carbon-14. And then I've provided you the half-life. Go. All right, did you get an answer? Hopefully you did. This is my favorite part of half-life calculating. It's something we actually use in science all the time, which is so exciting. Not that we don't use nuclear chemistry all the time, but nuclear bombs are not such an easy thing to just whip up in the lab, but this is something we can actually do. So now, what you have to do here is first set up a couple different ratios. So how I like to do this is have an alive section, have a dead section, and then basically your standard. So I like to set it up with 12 carbon over 14 carbon, or carbon-12 to carbon-14. And so let's do this for our alive section. Our alive section is going to be the 1 times 10 to the 12th over 1. This is standard. This is constant. This never changes while a substance is alive. This is something we assume that for all living, breathing species, they have this ratio of carbon-12 to carbon-14. Now, for our situation, for our problem, we have to look at the specific dead sample. And so what we know for this sample is that we have 2.5 times 10 to the 11th per every carbon-14 atom, basically. So what we need to do is figure out what this new ratio is, or new concentration is, relative to what happens when something's alive. So basically, you just solve this problem here. So you have 2.5 times 10 to the 11th, divide by 1 times 10 to the 12th, and you're left over with carbon-14. So your carbon-14 value here is 0.25. So what this means is that a quarter, or 25% of the original sample remains. So what that means is if you started with 100, then you went to 50, then you went to 25, we went through 2 half-lives. If we ended up with 0.25 or a quarter, that's when you are right here, 2 half-lives through. So now we told you that an original half-life is 5,715 years. We said that there were 2 half-lives that went through in order to get this value right here, the 0.25. And so that means that this fossil is 11,430 years old. How cool is that? Isn't that neat? Real world science, real world application. We can actually back calculate how old a rock is, or a fossil is. I think that's awesome. All right, I'm going to leave you with that. Have a great week. Take care of yourself and drink water.